Okay, we'll get started. So I have a bit of a pain in my back, as a result of which my movement is a bit limited. Okay, so the lecture is going to go a little bit slowly than what it used to be earlier. Maybe that's a good thing or a bad thing. We'll find out by the end of the lecture. And in the spirit of the class, I'm using multi-arm bandit to figure out which movement doesn't cause me pain and which movement causes me pain. And as a result of which, by the end of the class, I'll be at the optimal performance. Okay, so we were talking about Bayesian methods. Two things we talked about in the previous class was maximum likelihood estimator, where my theta hat t was max over theta in theta, the probability of x1 to xt, which is equal to the product of f of x j, j is also used, xl theta, L goes from 1 to t. So this is the density function. If in case you have a density function, if you have a probability mass function, then you can just write it like this. But each of them is completely fine. Let me say or max over theta. So in the case of probability mass function, this is the way to get theta hat t. In the case of density function, this is the way to get theta hat t. We did not talk about maximum a posteriori estimate, where you have a prior pi 0 in p theta, and then we compute pi t by or pi t plus 1 by using this rule. This is the Bayes rule, xt plus 1 given theta into pi t theta over summation this is the Bayes rule. And then my theta hat t plus 1 is argmax yes.
I'm not sure about this because I would believe it if you use pi 0
Yes.
for Bayes update, but not if you keep recycling the pi t's.
So the pi t's would form as prior at time t after you receive the information at t plus 1. So you start with pi 0, then pi 0. So for pi 1, pi 0 is the prior.
That's not the complete information. That's just the most recent one.
That's just the most recent one. X1, right? So you get X1, then you update the posterior, and then this is your a posteriori estimate of what's the best theta. Now, in case there is a density function, this equation looks a bit more complicated, but you can definitely find the expression in the in Wikipedia or any books on any of the books in statistics or probability. Okay, so let's consider a concrete example in order to make this more concrete in our head. So let's say I'm opening a juice shop at OSU. I'm selling packaged juice to OSU students. My target audience is OSU student, and I have no idea about advertising. I've never done advertising before. I have no idea about advertising. I don't know any of the OSU students. So as I'm advertising at various places, so I can advertise in department, I can advertise via email, I can advertise in student lounges, I can advertise on the quota bus, I can advertise on campus bus. Okay, so there are many places where I can advertise. Those are my arms. Those are the arms that I'm going to pull, which is I'm going to advertise at that particular location. Over time, I'm going to update on from where I'm getting maximum amount of sales, and then I'll start trying to advertise more on places where I'm getting maximum amount of sales. So that is maximum likelihood estimator, because I don't have any prior experience. In the second case, I actually happen to know a lot of OSU students. So I ended up asking them, okay, where do people tend to buy juice? Why are they buying juice? And somebody said, you know what, I see people getting bored on the campus bus. So that's why they are buying juice in order to drink while they are going from point A to point B on the campus buses. And then somebody else tells me, people are doing late night studies in student lounges. So therefore, they're having juice or whatever as a midnight snack in student lounges. Now I have a prior. Okay, I have a prior on where. So I've done some survey, or I have prior experience of advertising, and I kind of have this pi naught, which is uh, if you advertise in campus buses or if you advertise in student lounges, you are going to get more sales. On the other hand, if you advertise in department, nobody stays in department late up at night. So therefore, there's no point trying to advertise in the department, because the reward that you're going to get there is fairly small. So now I figured out that so now I have a prior on where I should be advertising based on the rewards that I'm getting at various locations within the campus by advertising at various locations. I'm going to update my prior, and then my updated estimate of theta hat could be taken as the argmax of pi t plus 1, which is the posterior at time t plus 1. So every time you update the posterior, it becomes prior for the next time step. Okay, that's what this update rule is saying. So is it clear when you would use MLE versus when you would use MAP? So in MAP, you need to have some prior experience, some prior distribution over which arms are going to be better and which arms are going to be bad. Okay. Typically, you get these priors through survey, through market survey, through experience of other people. So I think a few days back, when we were talking about multi-arm bandits, somebody said, I'm going to ask my friend where to shop from, right? So that's a prior. Okay, so you survey among your friends, and or you learn from their experience, and you get a good prior, and after that you can keep updating your posterior on the basis of that. Yes.
That requires a survey, not like a single person telling you, oh, I shopped here, because that's part of the prior. I only have like how much one is better than the other. It's not necessarily the other.
Right. So mathematically, you still have to put it in the form of a probability distribution over theta. So if that one person is a very trustful friend of yours, you probably want to put the entire weight on that particular theta and zero everywhere else, and that's completely fine. That's your prior, but then you still have to keep updating your prior with all the posteriors that you might observe over time. Okay. Ideally, it's not good to have complete weightage on a specific theta and zero on others. You probably want to have epsilon weightage on others, and yeah, so that way you will have some options to update that in the future. You won't get degenerate solutions where the denominator is equal to 0. So yeah, we want to avoid those situations. Any other question? Okay. So the first, yes.
So the XT here corresponds to actions, right?
XT here would correspond to the reward that you got.
Okay.
Yeah. So here XT is of course an abstract sort of vector denoting any update of the statistics, but any update. So in the context of multi-arm bandit, we are using this as reward signal. But this is a more general technique. It's studied in statistics for a whole variety of reasons. But we will specialize it for multi-arm bandit. So XT in our case would mean reward. And we'll be running this prior for every arm, and we'll be running the MLE for every arm. So that's what we have been doing so far, where we're using the empirical average which is our theta hat t, right? Empirical average would be our theta hat t, and that's what is driving our decision making by adding some constants to theta hat t, and not constant but some term, and come up with an index for every arm. Okay, any other question? Awesome. So the first, let's consider an example. So of MAP, because this is going to be important for Thompson sampling. So my reward model is one if with probability theta. So theta is between 0 and 1. So this is my theta. And it's 0 with probability 1 minus theta. So in the case of, and again, a lot of the stuff that I'm going to talk about was created in the context of, was studied in the context of advertisement system. And in advertising, people tend to focus, at least in online advertising, whether you click the ad or you did not click the ad. So that's why you have only two options, 1 or 0. Whether you click the ad and you got a reward, I mean the platform got a reward, versus you didn't click the ad and therefore the platform did not get any reward. Okay.
Sorry, that's the omega or alpha?
Which one? This one? This one?
I mean,
With probability.
with
Probability. Yeah. So this is known as Bernoulli reward. This is my Bernoulli reward with parameter theta. So theta parameterizes this Bernoulli random variable. And the posterior, assume that phi 0 is my beta distribution with parameter alpha and beta. Okay. So then the posterior phi 1 is going to be beta alpha plus reward, whatever reward you got, and beta plus 1 minus reward. So the posterior is extremely easy. This is known as conjugate priors. So you come up with a distribution that is parameterized by theta. When you update the posterior, so you have a prior of a specific type, you update the prior, it actually becomes an extremely simple update with respect to the random variable that you have observed, which is the reward could be either 1 or 0, right? That's what we mean. So reward could be either 1 or 0. So if it is 0, then your alpha remains alpha and beta becomes beta plus 1. In the other hand, if reward was equal to 1, then it's alpha plus 1 and then beta plus 0. Okay, so the update to the posterior update is a very simple process. And this is studied under the umbrella of conjugate priors. And you can look up Wikipedia. Wikipedia has a very nice article on conjugate prior. But I'm sure you can find these. The good thing about Wikipedia is you get a list of conjugate prior. So what is the distribution for the random variable and what is the update for the posterior based on the observations about the random variable. So they do this computation and they have created a table. So on Wikipedia, it looks pretty nice. And you can get a lot of information about conjugate prior distributions there. Okay. So this idea was exploited by Thompson in 1933, and then Yahoo researchers, and I'm forgetting the name, but 2010. So Thompson, I think, was working in the context of medical sciences with respect to the reward was, a drug was given and which drug worked and which drug did not work, something like that. I haven't read Thompson's paper, but I have read the Yahoo researchers paper back in 2010, and this Thompson's algorithm was used, was rediscovered / used multiple times over the years. So it's not like they got it out of the blue, but there has been a lot of work since 1933 and 2010. It's just that this particular thing, so what Yahoo researchers did was implemented Thompson sampling in actual Yahoo advertisement system, and they saw a huge boost in terms of the rewards that they were getting out of the advertising system, and that's why this paper kind of became pretty famous at that time. So this is known as a Thompson sampling algorithm. This is the multi-arm bandit algorithm. So I have n arms. So these are like n advertisements for a specific keyword. So I search for keyword juice, and I have like 10 different juices, whatever, orange juice, XYZ companies orange juice, and ABC companies celery juice, and so on and so forth. So I have n arms, so n such advertisers or n such advertisements for a specific keyword, and the reward for each arm, 1 with probability theta k and 0 with probability 1 minus theta k. Let's say my prior pi 0 k was beta alpha k beta k. So after t plus 1 time steps, this is the, maybe I should write alpha k 0 and beta k 0. So that's at time 0. That's what my prior looks like. This is alpha kt plus reward at time t, beta kt plus 1 minus reward at time t, such that I want to say utk is equal to 1. So I pulled the kth arm. In other words, I showed the kth advertisement to the user at time t, and the user clicked on it. So then in that case, reward is equal to 1. So I updated the alpha kt and beta kt for the kth advertisement. Otherwise, it remains the same. If my kth arm was not pulled. And then theta k t plus 1 equals is generated and you pull and then mu t plus 1 based on all the information received until time t is argmax theta k t plus 1. Or I don't want to say mu k, pull the arm. Yeah, this looks correct. Okay, so let's look at what this Thompson sampling is doing. I have n advertisements. My reward is distributed according to the parameter theta 1 all the way to theta n. Remember that the expected reward is theta k, right? Because theta k times 1 plus 0 times 1 minus theta k. So the expected reward is theta k. Ideally, we want to pull the arm with the maximum theta k at every point of time, but because I don't know theta k, I need to have some way to estimate the value of theta k. And at the same time, remember that we need to be able to do some sort of exploration versus exploitation. So we want to pull the optimal arm more number of times, and we want to pull the suboptimal arm roughly log t times at the end of capital T time period. So far what we were saying was, okay, I'm going to compute the empirical reward at every point of time for every arm. I'm going to add some term that depends on how many times I have pulled that arm in the past, and then I'm going to pick, that would be the index for that particular arm, and then I'm going to pick the arm with the maximum index. That was the algorithm in the previous lecture. Now in this particular case, what we are saying is, look, I'm not going to compute the empirical estimate of what rewards I got. I can definitely do that. I know exactly how to do that in the context of UCB algorithm and whatnot. But in this particular algorithm, I want to have a prior on my reward distribution. And the prior is of this particular form, that my prior would be a beta distribution. Because this is a Bernoulli distributed reward, I'm going to have a prior on theta as a beta distribution. And then I'm going to update the posterior at every point of time based on which arm was pulled. So I'm only going to pull one arm at a time. So I'm going to update the posterior distribution for that particular arm. For arms that I'm not going to pull at that particular time, I'm not going to update the posterior. It's going to remain the same as the prior at that time period t. Okay. Now I have the updated posterior for every arm. I'm going to generate another theta k at time t plus 1 according to this particular distribution, and then that becomes my index, and I'm going to pull the arm with the maximum index. And because I'm generating a random variable here, I'm automatically exploring, because sometimes the generated theta k could be smaller, sometimes it could be larger, as a result of which there is inbuilt exploration within this particular algorithm. So I don't have to use how many times I have pulled this arm versus not pulled this arm. All that information is not needed here. I just generate a sample, and then I pull the arm with respect, whichever has the maximum theta k, I'm going to pull that particular arm. The expected regret of this mu at time t is again O log t plus constant. This was proved in 2012 by Agarwal and Goyal, if I'm not mistaken. Okay, so Yahoo paper was 2010 paper was basically more of a, it was not a theoretical study, it was more of an implementation study that they did in Yahoo. They used advertisement as the arms, and they wrote a nice paper on what they observed in practice. And then finally the regret bound was actually computed in 2012 when it was shown to have locked the regret. Any questions so far? Okay, so the way you generally apply this particular algorithm, like the more general, you can of course come up with a more general reward distribution here, parameterized by some complex theta. But as long as you have conjugate prior distributions, then in that case the posterior update would become somewhat easy based on whatever reward you have observed. And you can do the posterior update. You can generate a new theta according to the posterior distribution. You can pull the arm with argmax of expected value of the reward for that particular theta. Okay, so remember in this case the expected reward is theta k itself. Okay, so that's why I'm using argmax. But in the more general case, you will have to use expected value of the reward with respect to theta k t plus 1. And then you can, if you want, you can go ahead and compute what the regret bound you are going to get for that particular algorithm. Okay, that's the general recipe. This is a very specific recipe for Bernoulli rewards and beta posterior distribution, but you can extend it to more general settings. And I don't think, I mean, I'm sure people have done this regret analysis for Gaussian rewards and for exponential family of rewards and so on. I just haven't read those papers, so I can't really comment on what sort of regret guarantees other people have got for different distributions. But just know that it can be done for other distributions as well, and it's a fairly old study, so a lot of papers must have been written since then, which extends this to other general reward models. Any other question? Any questions so far? Okay. The next algorithm is Bayes UCB. Okay, so now I have theta which lies in some real line. In specifically, it can be between 0 and 1. That's completely fine. I have the posterior distributions on theta, and I have the CDF. Everyone is familiar with CDF, cumulative distribution function. Okay, so I have CDF f1t to all the way to fnt, and I'm going to define qk okay, TP, this is the quantile function in x in R such that P is less than Fk Px. And then I'm going to define my index of kth arm at time t as qkt 1 minus 1 over t log t raised to c and c greater than equal to 5, and the regret O log t plus constant. So I have posterior distributions. I can come up with cumulative distribution functions for the posterior distribution. Then I come up with a quantile function. I use a similar, if I'm not mistaken, this should be TIT. Let me just check. Okay. This is capital T. Yeah, for some reason it doesn't depend on, so this T doesn't depend on how many times you have pulled that particular arm, but this is the horizon length, so log T raised to C, C is greater than equal to 5, and then based on that, you pull the specific arm, and the regret that you get is order of log T in this particular case. Yes?
So whenever the index depends on capital T, that means we have to know exactly how long
That's
we're
right.
running.
Exactly. Exactly. So there are a few cases where you need to know what the difference between the maximum reward and the second maximum reward is. We considered some of those algorithms in the previous lecture. And in this particular case, you need to know how long you're going to run this algorithm to be able to compute the regret. Any other question? Yes?
Why C should be like the greater than the 5?
It appears somewhere in the regret bound.
Okay.
Yeah. Many of these proofs are extremely long. I haven't gone through the proof myself, but these are very highly cited papers, so I assume the proof is correct. And that's, in order for proofs to work, they want C to be greater than equal to 5. I wish someone could write one paper which could write somewhat sort of general results so that you can compute the regret bounds of each of these algorithms in one shot rather than writing 20 pages of proof and bookkeeping. How many of you are doing PhD here? Okay, so that's on you. You guys have to do this work. Okay. The third algorithm I want to talk about actually comes from a community called adaptive control. How many of you have heard of adaptive control? Okay, a few people, especially people who are from Center for Automotive Research. They tend to use adaptive control quite a bit in automotive applications. So I want to cover that particular algorithm. It comes from 1982. For some reason, that algorithm has not received much attention in the reinforcement learning literature. So maybe this is the only RL class where that algorithm is being taught. I don't know. But, oh, I don't want to maybe erase this one. These are the only two algorithms I'm covering in this class. I'm on Bayesian approaches to multi-arm bandit, but by no means this is an exhaustive list. There are many more algorithms that uses Bayesian methods for multi-arm bandit. And if you're interested in this topic, feel free to reach out to me and I can point you to appropriate references. So, maybe a quick business question. So, we can always use multi-arm bandit to learn which one is the best advertisement or best whatever, creatives and so on. Then why do we need design agencies? Why do we need experts in advertisement to advertise stuff for a university or for a company or for Google or for Facebook? Anyone can give me an answer? Yeah.
You need a set of advertisements to run your.
Very good. So you need the N arms. So you need N advertisements and you want to see which one is doing best. Perfect. But maybe I can just recruit one of the graduate student here and ask him or her to make 10 or 9 advertisements for OSU.
It'll take a really long time and a lot of advertisements if you don't have a good initial set of advertisements.
Okay, I want you to build on that train of thought. So why do we need experts? Why can't we just ask some random person to create advertisements for OSU?
Because the experts have a good idea of what a good advertisement is.
Wonderful. Excellent. How does that relate to what we are talking about right now?
They are confident in their buyers.
Exactly. So experts have good pi naught, and that's why we need experts. Okay. So of course you can always have a graduate student or an AI system create 10 video advertisements for OSU that please come to OSU, you can get wonderful education and whatnot. But you still need experts who've done advertising for 20 years, 30 years of their life. You still want them to be there because they have a much better pi naught in comparison to me or you or any AI system. Or I would say right now the thing that Sam Altman is going around telling the rest of the world is that they have the best pi naught ever for advertisement and for everything in life. It still remains to be seen, but certainly experts have better pi naught than each of us, and that's why we hire experts to do things like advertisement and whatnot. Okay. All right. So the next algorithm is reward biased. Maximum likelihood estimator. And I want to draw your attention to specific papers. Borkar and Baraya, 1979, and Kumar and Becker, 1982. And then the third paper is Liu et al. 2020. So Liu is Kumar's student, and he wrote a new paper in 2020 extending this particular idea to the bandit setting. So whatever I'm going to talk about is from this particular paper. I encourage you to go and look at Liu et al. As to how this paper's ideas can be implemented in the multi-arm bandit setting. The reason I'm not considering this paper is because the equations are pretty complicated. But I just want to draw your attention to the main idea, the core idea of reward biased maximum likelihood estimator. And then hopefully you can read this paper and come up with the index policies for different types of reward distributions. Okay. So what is the setting? So I'm in the MDP setting. So not family of n alternative bandits. So I'm departing from the typical approach. So far we were talking about family of n alternative bandits, and then we were trying to figure out the index policy for those each arm. But now I'm not doing that. I'm going back to our MDP setting. So in some sense, this sort of bridges the gap between bandits and the MDP stuff that we were talking about earlier. So I have the transition kernel, which is P I J U parameterized by theta. And I think I should use small p here. For a policy mu, let's say P mu theta be the transition matrix. Of course, theta lies in capital theta. And let's say mu star theta equals to argmax mu average cost average reward Okay, so I have a MDP. I don't know the transition kernel of the MDP. I know that the transition kernel is parameterized by theta, and theta lies in this set capital theta. So I have a car running on the road. I don't know what the mass of the vehicle is. So mass is the unknown parameter. And the mass of the vehicle is affecting how the vehicle is moving on the road. Okay, so vehicle might be sluggish because it has a lot of, maybe there are 5 or 6 people sitting in the car and the trunk is completely full with stuff. So then have any of you driven a vehicle that is fully loaded? Like there are many passengers in the vehicle. Okay, one person. How does the car feel when you are driving the vehicle fully loaded?
Feels like when you push the pedal down, it doesn't go.
It doesn't go as fast, right? The acceleration is not very good, right? So, you know, the transition kernel of the vehicle really changes if there are more passengers in the car versus less passengers in the car. You can clearly feel it when you are driving the vehicle. Okay, so mass is an unknown parameter in the context of a car. Anything else? What other? Okay, the room, the air conditioning system of the room. So right now there are so many people sitting in the room. So therefore the air conditioning system has to work extra hard. But after this class, all of us will go out. The room is going to be empty. The air conditioning system doesn't have to work as hard. So theta is the unknown parameter, which is how many people are there in this room. How much energy are they emitting into this particular room? So that's the transition. So the transition kernel of the temperature, how the temperature changes in the room, is a function of theta, but theta is unknown. All right. If I use the policy mu, which maps the state to action, let's say P mu theta is the transition matrix. So far in the previous lectures, we only had P mu. We never had P mu as a function of theta. But now my transition matrix under a policy mu is a function of theta. And let's say mu star theta, if I knew theta exactly, if I knew what the value of theta is, I have an average reward problem. The reward function might be known here. So I have the average reward problem, and I can compute the value of mu star theta by optimizing the average reward cost using relative value iteration algorithm, right? And all of you have implemented relative value iteration algorithm, so you know how it works, how to compute mu star theta. So this was part of your assignment 2, and I think all of you have done it pretty well. Was it assignment 2 or assignment 1? maybe assignment 1, is when you computed mu star as a function of the transition kernel. Okay, so this is the setting. Now the problem is I don't have theta. So what should I do? How do I come up with? So I need to figure out mu, right? I need to figure out the policy mu that maximizes for true theta. I want to find, so the goal is find mu star for true theta. But true theta is unknown. So what would you do in this setting? You're driving a car, you don't know how many passengers are sitting in the car. You need to drive the car to your destination. How would you go about figuring out how to drive the car? Any thoughts? The answer is actually on the board. So I'm not putting any prior on theta. Okay, I don't have any prior on theta in this case. What would you do? Yeah.
You just test out different accelerations and then.
Okay, so you start with some policy mu 0, then you collect data. Which could be I0, U0, I1, U1, and so on. Let's say IM, UM, and then what?
I don't know if I'm driving like I feel like I could pretty quickly figure out if I need to press harder or not.
So there is some algorithm that's running in your brain where you are quickly figuring out how to run this vehicle. But I'm trying to create that more concrete. What is the algorithm in your head? So you're collecting data, then what do you do?
Update policy.
Sorry?
Update the policy.
How will you update the policy? That's what you want to do. Sorry? There is, I mean, what you are collecting is a data set. So certainly each UM is a function of IM because you're using mu naught to collect that data. Any thoughts?
I have a question. So,
Yes.
So although we do not know PI transition, but we know the formula PI because it's parameterized.
That's right, parameterized. Yeah.
So maybe we use MLE.
Okay, great. So you use MLE
And we will estimate the theta.
to estimate,
Theta hat first, then we.
let's say theta hat m. I don't want to use, maybe so this is going to be an episodic. So let's consider this is episode 1. And let's say this is theta hat 1. And then what do you do?
Already have that.
Okay, so then you compute mu star theta hat 1.
And we use it again. Yes.
Perfect. Okay, thank you. All right, so this is the algorithm from, okay, so this is a not a counter example, but this is a negative paper saying that this kind of algorithm has problems. And then this one corrected the problem with the algorithm. Okay, so let's think about what is happening in this algorithm. So how do you estimate theta 1? This is going to be theta hat 1 equals to argmax theta and theta product tau equals to 0 to m minus 1 or m minus 1 p I t I tau plus 1 u tau theta. For the sake of completeness, let's say I have some initial value theta naught, and then I'm computing mu star of theta 0. And then I compute theta hat 1. Okay, so Borkar and Varaya, what did they show? They showed as follows: this theta hat t converges to theta bar in probability such that p mu star theta bar is equal to p mu star theta bar theta naught. And they call it, I mean, not they call it, but this was known at that point of time. It was known as the issue of identifiability. This is adaptive control literature, so they are using control theoretic terms, not reinforcement learning related terms. Roughly, the issue of identifiability is not able to pinpoint the MDP parameter theta, the true MDP, the true MDP parameter. Okay, that's called the issue of identifiability. So I'm collecting data from an MDP. I'm trying to estimate theta hat t according to the maximum likelihood estimate based on the entire history of state action pairs that I have computed so far. Remember, reward is in this case known, so we don't care about the reward function. All we care about is the transition kernel in this situation. And so if I'm using an estimate, the maximum likelihood estimate of theta hat, in order to compute the optimal policy and use that optimal policy to collect the data and then update theta according to maximum likelihood estimator and then compute the next policy and so on and so forth, and I keep doing this, eventually the estimate is going to converge to some theta bar, and you would think that, oh wow, you know, my algorithm is converging to some theta bar, then it must be the true theta, it must be the true mass of the vehicle. But what they showed in the paper, what Borkar and Varaya showed in 1979 paper, is that you are converging to theta bar, which has the same transition structure under the policy mu star as the transition structure if the parameter was theta naught and the policy used what was mu star theta bar. Okay, so you're not able to distinguish between these two MDPs. You don't know which MDP you are solving, and that's the issue of identifiability. Right, so the transition structure with the mass that was estimated is the same as the transition structure with mass that you initially started with, the initial estimate of the mass. So you don't quite know what the true mass of the vehicle is because you can't identify between the two. All right, so that's the negative result. This was the negative result. So, and this, by the way, this controller is known as certainty equivalent controller. Okay, so theta hat is my estimate. I'm going to compute the optimal policy with respect to that estimate. that's my certainty equivalent controller. It's just a terminology used for. So if you look at some older papers in controls and they say certainty equivalent, all they mean is they are estimating some parameters and they are computing the optimal policy with respect to that parameter, and that's their certainty equivalent controls. It seems fairly normal, by the way. I'm not disputing it. It seems fairly normal and usual to estimate something and then use the controller for that particular estimate and expect that things will work out fine over long periods of time. And that's how that's a fairly reasonable algorithm. I'm not going to say that it's unreasonable. What they showed was it's unreasonable in the context of MDPs. So this was a negative result, and that's why it was an important result. So then Kumar and Becker came in 1982, 3 years later, and said that, look, we can actually correct for this problem. And they came up with reward biased maximum likelihood estimator. So what they said was, I'm not going to touch this certainty equivalent controller. I'm not going to touch this data collection process. All I'm going to do is change the likelihood estimator for this theta hat. So what was their algorithm? So now I'm talking about Kumar and Becker. So I have J of mu star theta bar is equal to, because of this result, what I have is, or maybe this equality is J of mu star theta bar theta naught, which is less than equal to J of mu star theta naught theta naught. Okay, so if the transition structure is the same between theta bar and theta naught, then the expected reward is expected average reward is going to be the same, which is less than equal to the expected average reward you would have gotten if you had started with theta naught and you had applied this particular policy all the time. Okay, this is some other policy, not the optimal policy. So therefore, there is a less than equal to sign because this is the optimal policy for theta naught. That was my initial guesstimate. So I see there are like 4 people sitting in my car. I just multiply 4 into 100 kilograms each. So therefore, it's 400 kilograms. That's a rough guesstimate. And you started applying the policy with respect to optimal policy with respect to 400 kilograms. Turns out that the average reward you are going to get is going to be greater than equal to the average reward you are going to get with theta bar, which is the policy that you which is the parameter that you converge to at the end of your learning process after infinite number of iterations. So remember that the average reward for the initial time is better than the average reward at the terminal time, like after the training is complete. Is that a good thing or a bad thing? Very bad. Okay. You might have as well just kept using the original policy and you would have achieved a much better average reward than to try and optimize it. Okay. So that was the starting point of Kumar and Becker. So they said that, look, if you want to optimize an average reward problem and you are seeing this particular situation, it's not a good situation to be in. So probably my theta hat 1 is, the way I'm computing my theta hat is actually faulty. So then they came up with the reward biased maximum likelihood estimator. This is MLE, okay? This is the vanilla MLE. There's no reward here, okay? This is just the transition structure giving you theta hat 1. Now I'm going to bias it with respect to the reward that I'm getting. So this implies, in particular, this implies that my parameters are biased to non-optimal rewards. So the authors are saying that because you are observing this kind of situation, what it essentially means is that the parameter estimate that you are computing is getting biased towards non-optimal reward, as a result of which the reward is actually, average reward is reducing. So how do we fix this? That's their algorithm. Okay, everything remains the same. Now my theta hat t is argmax theta in theta f of j mu star theta theta raised to alpha t product tau equals 0 to t minus 1 p I tau plus 1
and alpha t, they are any functions.
any functions. So f is monotonically increasing function, strictly positive, and alpha goes to infinity, but alpha t over t goes to 0 as t goes to infinity. So something like alpha t could be something like log t or something like that. Okay, and then they proved that if you use this particular way to bias the maximum likelihood estimator to compute theta hat t and then compute the optimal policy, you will converge to the optimal theta star, which sorry, the true theta towards the end of the learning process. So that was the main result of Kumar and Becker. And then Liu, who's Kumar's student, so Kumar is now a faculty at Texas A&M University. So his student ends up, so remember this is for an MDP setting, not an N alternative bandit setting. So what he did was he studied how do you specialize this algorithm for N alternative bandit setting. And then he showed in his paper that it leads to index policy in a variety of multi-arm bandit settings. Okay, so I'm not going to cover those algorithms. The expressions are somewhat difficult, but the core idea is this particular idea, which is if you're collecting data and using maximum likelihood estimator in the context of Markov chains, Markov decision processes, then you suffer from identifiability problem, which means you end up converging to theta bar, which is non-optimal, which is giving you non-optimal reward. So in order to correct for that, you have to bias the maximum likelihood estimator with respect to the reward function. So that's why this is a reward biased. Okay, so I'm biasing the max. So this is my maximum likelihood thing. I'm biasing it with respect to the reward, but the bias has some specific function form in order to correct for this biasness of parameters to the non-optimal rewards. It's correcting for it. So it's giving more weight to the optimal rewards actions and less weight to the non-optimal reward parameters. And that gives you a estimator which eventually gets you to the right value of theta bar. The important thing to note here is that I'm letting tau go all the way from 0 to t minus 1. So even though I'm doing episodic learning, I'm using the data sets all the way from time 0. I'm not discarding the data sets from time 0. Okay, so I'm using the entire data set in order to compute theta hat t, and yeah, this one seems to have the reasonable performance that you would be expecting. Yeah.
So is your MLE dependent on the policy given the data that
Absolutely, because the policy is generating this data set, and that data set is being used to compute theta hat 1. So for sure.
I was using gradient descent to find this MLE. I would have to reevaluate the policy every gradient step.
Yes, in order to compute this, right? Yes, definitely you will have to do that for sure. Depends on the setting, right? So that's why they specialize this. Okay, so in 1980s, people weren't worried about computational complexity of algorithm. That wasn't something that people cared about. But in 2020s, people do care about it. And so they specialized it to multi-arm bandit, and they showed that there are simpler algorithms to compute theta hat t, which leads to easier to implement policies in system. Yeah.
But why people in 1980s like they do not care about the complexity?
So the question is, why didn't people in 1980s, why didn't they care about computational complexity? Anyone has an answer to that question? Yes.
They were theorists.
They were theorists. That's right. So they used to do theory research. It didn't matter. In theory, it doesn't matter what the computational complexity is. As long as the proof works, it works. You know, you can write papers about it and you can graduate. That's what I did when I was a PhD student too.
But during that time, I mean, the computer is not as powerful as right now, right?
That's an excellent point. So at that particular point of time, all of this was implemented on analog devices. I mean, if at all, so they didn't care about implementation, but whatever adaptive controller was supposed to be implemented, it would be implemented in analog devices. And in those devices, there is no notion of computational complexity. I'm not saying that it's you shouldn't worry about it, but it's a bit complicated to discuss topic, because how quickly the analog devices are going to work depends on the lead lag compensator and the PI controller and the settling time and this time and that time, all of which you've studied in 3550. I mean, I'm assuming some people might have taken 3551 and they know how to make analog devices converge faster using lead compensator and lag compensator. But if at all somebody was coming up with algorithms of this type, they were hoping that somebody will create an analog device and put it in an actual system and then it will work. But they weren't careful about how much time it's going to take to compute this stuff. Even stochastic approximation that was developed at that time, it's an infinite horizon algorithm. You don't have any guarantees for finite horizon. It's the finite horizon thing has started rather recently. to understand the complexity, sample complexity of stochastic approximation algorithms and such. So all of this is somewhat modern phenomena, not an old phenomenon.
Just a quick question.
Yes.
For the J, can I understand it as V with the state value of the first of the start state? Is it okay?
That's right. That's right. Because this is an average reward problem, and one of the assumptions in Kumar and Becker paper is that all states are communicating with each other.
Oh, it's only for average.
It's average. It's an average reward. So I had mentioned it in the previous.
Oh.
It's an average reward problem.
For infinite horizon.
For infinite horizon, average reward.
Okay.
This is infinite horizon, average reward with parameter theta.
So if it's discounted, it may not work.
If it is?
If it is discounted, the MDB.
You know, I don't know whether. So in one of the assignments, I think in assignment 2, I had given you the question about converting. No, I don't think average reward and discounted reward has some connection, or maybe they do. I don't know. I think you will have to go back to the paper and see whether the entire proof will work for discounted or not. I cannot say for sure if it's going to work. Okay. Phil, you had a question?
No, I would answer.
Okay. Any other question on this? Okay. So this gives you, again, the other thing that I wanted to mention is this particular algorithm, maybe it has like 100 or so citations, and a few papers have been written so far on this particular algorithm. The reason for me to cover this algorithm was those of you who are hunting for reinforcement learning problems for research. It's a good problem to figure out how can we learn from this class of MLE estimates to come up with reinforcement learning algorithms. I think this is an underappreciated area of study and something that if you are looking for a research problem could provide you with a good research problem to think about. Right. So the next, I still have 7 minutes, so I want to make use of it. And it transitions me to the next topic, which is, by the way, again, in this particular paper, they have shown that the regret is order of log t plus constant for the multi-arm bandit setting using this algorithm. So it has some reasonable properties. And the reward models in this particular paper are exponential and Gaussian and so on. So it's more general reward models than 0-1 reward models. Okay, so now it leads me to the next topic, which is, so remember in multi-arm bandit, we have n arms, and the state of these n arms are either IID or according to a Markov chain. Now the question is, can we extend this whole notion of regret and the notion of I want to come up with a learning algorithm for a regular MDP. So I have a regular MDP, not a family of n alternative bandits. So I have a regular MDP. I want to be able to learn the optimal policy as soon as possible, as is the case in multi-arm bandit algorithms. So the question then becomes, I'm collecting data sets from this MDP. So I'm running a car just like this particular situation. So the only difference between this situation and the UCRL2 algorithm is that here the reward function is known. So once you fix theta, you know what the transition kernel looks like, and you can compute this particular, you can compute this policy, or you can evaluate this average reward. But now let's assume that you don't know the reward function, you don't know the transition kernel. You don't think there is any parameter that drives the transition kernel. So there's no parametric model of the transition kernel, but you are in a finite state, finite action setting. You are collecting data sets of this type, including the reward. So you have R0, R1, Rm, and so on. And the question is, now that you are collecting all this information, how are you going to compute the optimal policy, and what sort of regret are you getting by computing the optimal policy? So going back to this setting, what would you do? While I erase the board, think about what would you do. Now you're getting this state, action, reward, state, action, reward, state, action, reward, state, action, reward for infinite horizon. I mean, not infinite horizon, but you're getting it. And you can then pick a policy, and then you can collect more data, then pick a policy, then collect more data. How can you minimize the regret? So what would you do? Any thoughts? So I'm collecting all this data from a Markov chain, from a Markov decision process. So I have a simulator. I can send a policy in, and it's going to generate this data set, and it's going to give me that data set. And now I need to figure out what should my next policy be. And I want to minimize the regret. So remember, in the previous case, when we were talking about policy iteration and value iteration, we were only concerned about convergence at the infinite time step. Now I don't have infinite time steps to learn. I want to make sure that my regret is as small as possible. Okay, so what would you do in this setting? I want thoughts. What would you do? Nothing? Okay. Anyone else?
So our objective is not maximize the values, state value, but
I don't want to wait for infinite amount of time to get my optimal policy mu star. Now I want to minimize my regret. I want to get regret. I want to get probably log t regret at the end of time step capital T.
Be regularized with if with regret.
if it is if it is FM, it becomes Q learning.
No, but Q learning also converges in infinite horizon. So all the algorithms, remember everything we talked about in the previous, like pre-multi-arm bandit, everything converged at infinite horizon. So as t goes to infinity, Vt converges to, or V hat t converges to V star, pi hat t converges to pi star, whatever, Qt converges to Q star, and so on and so forth. But it's not minimizing. I don't know what's the performance is at t time step, and specifically I don't know what the regret is after t time step. So what do you think you will do in this setting? Okay, so this is the algorithm that was developed in 2010 called UCRL2 algorithm. So I'll talk about UCRL2 algorithm in the next class. What they do is, based on this, they come up with an estimated transition kernel and an estimated reward function. They construct a ball around the transition kernel and the reward function, the estimated transition kernel and the estimated reward function. They pick the worst MDP within those balls. Okay, and then they simulate that worst MDP with the updated policy. Okay, and then they make those balls smaller and smaller, and eventually you have the minimum, like the regret is minimized in that particular case. Okay, so that's the algorithm we'll be talking about in the next class. All right, thank you.